This is Csaba Szepesvári recording from Edmonton. I'm jointly affiliated with DeepMind and University of Alberta, and this talk is about myths and misconceptions in reinforcement learning. Thanks for the invitation to this Deep Learning Day at KDD. I'm delighted to deliver this presentation, although it would have been much nicer to be there in person. So first and foremost, I'd like to thank my colleagues at DeepMind and the Aralia group who have contributed with numerous ways, ideas, criticism, and so on and so forth to this talk. So I'm truly grateful for their help. So with this, let's get started. So as I said, this talk is about myths and misconceptions in RL. And I saw that this is kind of like the right time to start the discussions and opening a dialogue about this. Because RL is growing really fast. A lot of people are looking at RL. And maybe RL is not so easy to grasp as a field. Because the literature is, frankly, probably lacking. There's so many papers coming out, it's really hard to keep up with the literature. And so this might lead to, like all kind of myths and misconceptions to spread within the community or even outside of the community. And during the many years while I been working on RL, I've heard many of these myths and misconceptions. And so I said that maybe it would be fun to put together a presentation about this and then start a discussion about them. So with this, let's get started. So the contents has two parts. First, we are going to look at RL from a bird's perspective, a little bit from the outside. Where someone might ask the question, should I get into RL? Or looking at RL, they may be thinking that, oh, RL is really problematic. And working in a neighboring field of RL, they might feel that RL is maybe stepping on their toes. And like, what's really the situation there? And so I'm going to talk about myths and misconceptions related to these topics. And then I'm going to end with some meta considerations that are somewhat specific, but not necessarily ultra specific to reinforcement learning. All right, so the way the presentation is going to go is through these cards. I'm going to have two types, the myth card and the fallacy card. There is very little difference between the two. Myth is just a wrong belief, and so every myth card is going to state what I think is an incorrect belief, and then I'm going to try to digest into where this myth might be coming from, and then talk about how to correctly think about the underlying issues. And the difference to fallacies is the fallacy is a myth that is a result of faulty reasoning. And here I add 1 point, which is going to talk about what's wrong with the arguments that are leading to this incorrect belief. So these were, by the way, inspired by design patterns and anti-design patterns, which I like very much. I hope that you're also going to like this type of way of talking about myths and misconceptions. All right, so first part, should I get into RL? So first of all, what is reinforcement learning? Our first myth is about that reinforcement learning is just a specific set of algorithms like temporal difference learning, deep Q networks or Q learning, PPO, and some other algorithms like evolutionary search or random search, or some parts of self-supervised learning are not reinforcement learning. And then so the distinction is that there are algorithms which are reinforcement learning algorithms, and there are algorithms which are not reinforcement learning algorithms. And I would trace this back to the literature and the lack of literature that would properly discuss what most of the people practicing RL for a longer period of time hold, which is the view that RL is not a specific set of algorithms that would be evolving over time anyway. So it would be a very, very vague definition, but it's a set of interrelated problems which may have this specific set of algorithmic solutions. So that's the quick resolution to this. And here it's important to point out that RL is not a single problem, although it may look like if you look at just one particle type of paper or book. But there are three interrelated problems, and maybe there are many more variations of them. So the three most basic ones, I would say, are online reinforcement learning. So in online reinforcement learning, you have this agent interacting with its environment. The environment is initially unknown or partially known, and the agent's learning about the environment, but not for the sake of learning, but for the sake of collecting as much reward on the long term as it can get. So in this setting, the criterion for an agent is how much reward it collects over time on the average or in total and so forth. So there are various variations of this problem. So the next setting is batch reinforcement learning, where you have a batch of data. And this is practically highly relevant in a lot of applications. We do have data where someone was interacting with a controllable system and collected the data. And based on the data or wishes to discover some way of controlling the system such that if you're deploying this control error policy on the system, then on the future on the system is going to perform well. So that's the second setting. And the third setting is kind of serving the purpose of like helping with the first two settings. So it's not really a problem on its own, but it's a sub-problem of the previous two problems, which is planning and simulation optimization. So here you have, let's say, a simulator, and you can interact with the simulator. You pay with your time, with your compute, and you want to get the best possible policy with the least amount of computation and least amount of total simulation time. So here, this is a purely computational problem. So, all right. So with this, let's move on. People coming to RL also look at RL and say that, hey, you guys are talking about like running this policy on a real system that is going to be run in a feedback loop, and hey, that's totally super dangerous. Don't do it, please. Because when you have these feedback loops, then you can have this runaway phenomenon and really bad things can happen. It's really hard to understand these feedback loops. And so we better avoid this. And so RL is kind of like an ill-posed approach. So for people who hold this view, if anyone does hold this view, maybe this just exists in my mind and it's a caricature of what might someone think about RL, that this is just playing ostrich. If you have any machine learning system that takes some data, eventually maybe the machine learning system is going to be deployed in a real system. And when that deployment happens, then maybe there are going to be these feedback loops in the real system, even though the supervised learning or whatever learning component you had didn't care about these feedback loops. So the feedback loops are there or they are not there, regardless of what you're thinking about the problem. And if there are feedback loops, it's better to think about the feedback loops than not to play not to think about the feedback loops and play ostrich. So the resolution is just think about the feedback loops. You better start with this and then maybe just switch right away from supervised learning or anything what you do to reinforcement learning is super important. And you should also embrace the idea why you're doing this of online adaptation. I see a lot of people are raising eyebrows So that's the second biggest thing that you could have, that you let your system learn online. But hey, like if a system just memorizes something, that's kind of learning. So I would say that learning is actually quite common. Maybe we're not used to thinking about these online learning systems, but maybe this is not much worse than not learning. And actually, there is potentially a lot that is left on the table if you don't let your system to learn online. We all know about that. If you can run controlled experiments, randomized controlled trials and whatnot, you can learn much more about an unknown system or word than without running those experiments. And that is online learning, even though it's not trying to maximize cost, but it's trying to maximize information gain. So with that, it's also important to point out that, yes, feedback loops could be dangerous. And for that, you should think about them, and you should think about a proper way of assessing the performance of the systems that work in feedback loops, and how we should be thinking about these. And this leads to the next myth, which is that people do realize this, and then they start to write papers that start by saying that, hey, like, look at my system, and I have this proof or this empirical claim that shows that this system is going to be safe if you're deploying it. Well, I think that these people have very good intentions, and this is an important problem to work on it. But we have to realize that these claims have a limited scope. So why? Well, it's because all of these proofs do have conditions. And if you're running some experiments on some simulated system, let's say, how do you know that the real system is not crucially different from your system? You really have to think hard about differences between what you can prove or what you can demonstrate with simulation and what the deployment scenarios are. So the absolute statement that, hey, like, this is the way to guarantee safety, I take those with a big amount of grain of salt. So what's the resolution to this? Well, safety guarantees are still important. So I'm not saying that everyone should stop this research. This is super important. But you always have to think about the conditions. And that is general advice. The conditions tell you a lot. Well, here you should also understand that sometimes the conditions are simplifying. So you have to maybe also dig deeper into thinking about in what way and what parts of those conditions actually do matter for some result. All right, so enough for safety. So the next concern for someone who may be looking at RL as a potential future field to move into is that, well, if you look at the literature, time to time, there's going to be this headline or blog post or some paper appearing in Nature that claims that, well, RL algorithms are superhuman again, and they're doing so greatly, and you might have the impression that RL is basically done. We have solved all the problems. And indeed true that RL had a lot of successes, and that's great. But the actual resolution of this is that, there's still a lot ahead of us. So, for example, if you just take this claims that specifically RL is superhuman on Ethereum, and there's been some papers that were pointing out that maybe the way these comparisons are done to humans is not completely fair to the humans. Because, for example, the human score on tennis in these comparisons is negative. Well, yesterday I tried to play tennis and I have to admit, this is my score was negative too. But I didn't go beyond 5 minutes of playing because it was so boring. So it might be challenging as well to see what a skillful human would do, or an interested human would do on games which are maybe like too simple. And so what's the conclusion here? So we need to be honest about that we still have a large room for improvement. Superhuman performance is a long way. Yes, everyone should start to pay attention to reinforcement learning, because it's going to be important, and lots of open problems. So you should maybe start working on this. All right. People also, of course, they might approach reinforcement learning from practical perspective, and then they might download a package and then try it on some setting, and then they will cry out loud, RL just doesn't work. It's hard to make these algorithms work. The learning curves are going up and down, and so on and so forth. So why should I work on RL? RL doesn't work. Well, for these people, I would just say reinforcement learning is not equal to the current set of methods. This is interrelated set of problems. And there are actually use cases which are very inspiring, where RL algorithms achieved results which could not be achieved with any other ways. So they can work. But with that, yes, there is a lot of room for improvement. So this seems to be a recurring theme in this talk. And that's why it's a good field to move into. It seems that this talk is becoming a recruitment talk. I don't know. It just maybe it's a good field to move into RL. What can you do? But some people may object that, well, this field on its own, if I look at the papers, is highly problematic. So what are these issues? And we are going to look into ourselves here a little bit. Who we are practicing reinforcement learning and maybe potentially making all kind of mistakes. So one of the complaints that can be heard from inside and outside of the community is that in RL, people are just testing on the training data. So what do people mean by this? They simply mean that we have these simulators, and we like to run these experiments on these simulators. And whenever we work out an algorithm, then we are going to use the same simulator, maybe the same settings, the same randomization in the simulator that is used for tuning these algorithms or working out these algorithms. So I have to point out that it's just not just hyperparameter search, but whenever you're choosing between different algorithms, then you're kind of really testing on a training data. It's not really the data, but the training setting and the test setting is kind of the same. So the resolution about this is that you should just be clear about your goals. So some of these papers, I really want to solve the simulation optimization problem. And maybe sometimes the simulation optimization problem, that is this planning problem, is the right one to solve. So sometimes you can use as much compute as you wish, and you're just interested in the highest possible score, or the best possible way to play the game of Go or StarCraft. And then we don't really care about whether like the algorithm that we develop is going to generalize to the next setting. Although if you do your research well, and I think a lot of times people who are pursuing this type of research also think about this carefully, they want to develop algorithms that will be deployable for other settings, even though this is maybe not guaranteed and cannot be seen from the results on their own. So the next thing is that if you, on the other hand, have a different problem, so maybe you want to solve an online learning problem, or you have a batch problem, then you have to choose the right way to measure success, and choose the appropriate metric for that. And finally, if you if you have all these hyperparameters and then you're reporting results with the best hyperparameters found, consider reporting instead of that. Or in addition to that, doing a sensitivity analysis as well as you can do. I know that it's hard to do that, but more information is always better than less information. I really like to see the sensitivity analysis in the papers. They mean a lot, and usually you can learn much more from this than by just looking at high scores. So this leads to also the next topic, which is related to this testing and the training data, that some people just say that, well, hey, generalization in reinforcement learning is not even well defined. And again, I would blame the lack of proper literature about this problem. But the resolution is super simple. So the original meaning of generalization is that, well, on an unforeseen future scenario, you're going to do well if you were doing well on some scenario that was to some degree under your control. So you can play the same game in reinforcement learning. There is no magic to this, but generalization definitions are going to just look like as these different specific merit criteria. Like in online learning, it would be the total reward, or if you want to normalize by comparing to the best possible in hindsight, then it would be minimizing regret, pretty much the same thing. Or in batch learning, it would be the quality of the policy to be deployed, which will be really hard to measure if you're reading a batch learning scenario. And in planning, it would be the total compute used and the suboptimality, the policy that you came up with. So just use this for your assessment. And so these criteria are very well defined. So all of these problems are well defined. There is no problem with undefined problems in reinforcement learning. People also oftentimes remark on that related to the previous is that area just focuses on simulation optimization. And some people actually make the claim that this is the right thing to do because mostly we just have simulators. Then, like, why would you want to do anything else? Like most of the deep learning papers these days are using a simulation optimization approach. Then why would you want to evaluate your algorithms in a different way? Well, for these people, I just say that, well, this is very much as what's shown on this cartoon when the tail is wagging the dog. It mixes up what is easy to do or to publish on with what matters. So you should first and foremost think about what matters to you. So maybe simulation optimization is useful to you, but maybe it's not. Maybe you care about robustness and adaptivity or batch reinforcement learning, and then the criterion has to be different. That game is different. All right. So some people would also say that reinforcement learning is barking up the wrong tree. So maximizing the total reward is not the right problem because the optimal policy could be sensitive in various ways. So this is a fallacy because it blames the objective for underspecifying the problem. So if you're worried about, for example, observation errors or other uncertainties in your problem definition, just please include those into the problem definition. And then if you solve the resulting problem, then maximizing reward is not a problem. Like, that's fine. You just have to include these other conditions, which may change radically and will change most of the time radically the type of solutions that you're reading out. So you should include all the knowledge about the problem into the problem specification and just solve that problem. And in particle optimization is fine. maybe you need some variations of this problem. So you might also object to that, like there is a single reward function. Yes, there exist multi-criteria versions of reinforcement learning and so on and so forth. So you have to look sometimes a little bit beyond the most basic settings. So next, a lot of people trying RL or just looking at papers are going to say that, well, it's so incredibly compute and query intensive. The sample complexity is up in the sky. Empirical results are really disappointing. Reinforcement learning is just like this big snail. So again, this is just playing ostrich. If you want to shy away from a problem just because it seems hard, that's usually not what you should be doing. If you have an RL problem, just treat this RL problem. And maybe you have to swallow that sometimes RL is going to be really hard, but work on the niches then, right? So the speed is going to depend on many things, like how the problem is set up, what algorithms are there, how you're measuring performance, and so on and so forth. So the resolution is that you need to understand how to navigate the space of RL problems, and then find the niches where you can get these efficiency results that we all need. So, all right. Related problem is that RL is a bunch of algorithms, which is of course not true. So, so the final section of this perspective on RL is what our neighbors might be thinking about RL. So occasionally, and here I'm referring to one blog post by Ben Recht that he put out quite recently. Algorithms are compared to reinforcement learning. And for example, in this blog post, Ben was pointing out that on a recent workshop, Martin Riedmiller and a colleague of Ben, Francesco Borrelli, been talking about kind of the same problem. And Martin was showing a reinforcement learning solution that took 3 days to train, and eventually it manages to put there's a ball in a cup problem where you have a robot arm and like there's a string, a ball attached to it, and then you have to swing the end effector and make the ball enter the cup that is attached to the end effector. And the cup is really big in the case of Martin, and reinforcement learning requires 3 days and stereo camera system and so on and so forth. And Francesco's solution, on the other hand, is one shot, like after one trial with MPC and good old knowledge of Newtonian physics injected into this solution. You're able to solve this task, which a much smaller cup is a single camera system. So so what's the deal here? I say this is kind of like again comparing apples and oranges. There is scope mismatch between the general purpose, as general as possible, right? Approach that Martin is trying to pursue. Is not really interested in solving the ball in the cup problem, which you could solve with other techniques, and that has been demonstrated many times in the past with other techniques. But he's interested in developing these techniques that have the promise of being general and being applicable to other things. Of course, we are at the very beginning of this potentially long tour. And so we are demonstrating, or Martin is demonstrating his algorithms as a good scientist would do on a simple case for which we actually know the solution, so we can compare. And we see that, okay, there is some price to be paid. But maybe if you compare that price, maybe that will be hard to compare with all the engineering and other type of knowledge that needs to go into an really effective and efficient solution like Francesco's solution. And then question is whether that solution would generalize to something much, much more complex, where you don't just have, a ball that flies in the air, so the dynamics is kind of super simple, but you have friction, you have touch, you have faulty sensors, and so on and so forth. So there is a scope mismatch between these techniques that are being compared here. And also, of course, reinforcement learning might appear really bad if you just take some current set of algorithms and you compare it with some other algorithm. But RL has a big potential, and it's not equal to the current set of algorithms again. Keep going back to this point. So it's true that RL is not going to be the answer to everything, and then you should learn about alternative solutions. And if you care about solving a problem, then definitely think about the specifics of those problems. But we should also recognize the strengths and the weaknesses of these alternatives, as well as of the RL techniques. We do a good job, then we'll be much stronger together than otherwise. All right. So related issue maybe is that some people looking at RL might think that well, it's related to that RL is really slow. So while there is no reward, the reward is 0 all the time. You still want to learn something, and then maybe that's learning, like when you don't see any rewards, is not really the job of RL. But you could use other techniques like self-supervised learning, and you should be just aiming for learning good models, even without rewards. This is not necessarily a bad idea, but there could be some problems with it. So first of all, just because your reward is sparse doesn't mean that there are no RL type-ish solutions that you can think about that would shape the models even before you see reward and learning is over. So approaches that follow this path include nu0, UCRL VTR, and Agent 57, which think about this. So Agent 57, for example, thinks about this no reward problem, pure exploration problem before saving the reward, and sets up goals for itself. But still, whenever the reward arrives, start to think about how to schedule aiming for more reward as opposed to just pure exploration. And the other problem is that undirected model building may be super risky. So here I'm showing a screenshot of an Atari game where you see these little speckles, and then there are, I think, bombs, and you don't see it on the screen, but in this video game, these lines are moving towards the agent. So if you're not doing the modeling, the unsupervised learning in a careful way, then the whole background is moving, and then you might end up modeling a lot the irrelevant lines and missing the little bullets that are going to reach your ship. And that indeed has been observed many times. It's really hard to get things right when you have small things in the environment that appear, like as maybe almost like noise, but they are super important because it's a question of survival or death. All right. So what's the resolution? So learning good representations is a key. You can mix, and you should mix self-supervised learning with reinforcement learning. And actually, reinforcement learning can direct how you should be doing self-supervised learning in an active way. Learning passively about the environment is much less efficient than learning actively. And it's a sub-area problem I didn't mention the first 3 set when I was talking about the first 3 basic problems, but it's an area problem to learn to gain the most information, the most skills about an environment in an active manner. And you can also mix pure exploration, this way of just aiming to gain more information with exploration, which cares about the rewards as well. Another neighbor is people looking at causal reasoning, and they might look at reinforcement learning with suspicion that other people are just ignoring all the causality literature because RL has its own language and people are not really willing to change that. Maybe just stick to their language, and this is very different from the language used in causality literature. So what's going on? So does reinforcement learning ignore causality? Well, I wouldn't say it does. It just has a different language to talk about causality. You just talk about PUMDPs. It's pretty obvious that PUMDPs have the depth and the breadth to describe a lot of what the causal inference literature is talking about. Maybe it's not the most suitable if you care about causal reasoning. It's not going to be very convenient to use that language, but maybe it's not a bad language if you're thinking about this control type of problems. And also, batch reinforcement learning of policy evaluation has been mentioned before, but of policy optimization as well, is all about causality, right? Like, it's all about reasoning. Given this batch of data that I saved on my disk, if I went in, I deployed this other policy that was not used for collecting the data, it would take these interventions in the world. What would be the outcome of that? What would be the reward that I would incur in that case? So that's what batch reinforcement learning is about, or it's about even more optimizing for finding a good policy. So there's a huge overlap there, and I think reinforcement learning researchers are acutely aware of the causality literature, and we would be willing to use the tools, and I think that people are actively exploring of using these tools. But if a paper is not using the language of causality, that doesn't necessarily mean that it's not using any causal reasoning. So let's not be too specific about these languages. It's nice to be multilingual. We should learn each other's languages. We're going to be just better that way. All right, so now on to the meta myths that go beyond reinforcement learning. So, so the first meta myth is one of my favorites. A lot of times you go into literature and then people like to talk about that, oh, there is this curse of whatever, like curse of dimensionality these days, curse of horizon, all kind of curses. They are really popular. Curse is a scary word, so people like to use it for describing some insurmountable difficulty. So that goes back to probably Bellman, who noticed that for most of the problems he cared about, the number of state variables would grow exponentially with the number of relevant quantities, dimensions, whatnot, in the problem description. And as such, it was really hard to use simple algorithms in that setting, and you had to introduce something called functional approximation there. So functional approximation these days is done using neural networks. And indeed, functional approximation allows compressed representation, and as such, it has the hope of avoiding enumerating all possible values, right? So no one really thinks that you should be enumerating all possible responses or all possible values in supervised learning, same thing in reinforcement learning. And so hopefully, maybe that's going to break the curse of dimensionality, that we have to deal with these high dimensional spaces and whatnot. But does it? Well, the fallacy is that if you have a real curse, and many times you do, you just have to read the papers that are rigorously proving lower bounds. That curse, by definition, is unbreakable, right? So no one's going to break it. It's not going to go away just because you're waving a magic hand and throwing in some neural networks here and there. So then how to think about this problem? Because then it seems that I'm saying that you can't make any progress. No, that's not what I'm saying. I'm saying that what happens when you throw in the neural networks or function approximations, so that started with Bauman actually, then what happens is that you're changing the problem. So you can't break the curse, you change the problem setting, and then you can do something. So whenever we think about function approximation used together with reinforcement learning, we're thinking about the cases where the function approximator has the capacity and the capability to solve the underlying approximation problems in an efficient way, using it almost like as an oracle. And then we ask the question, okay, if we have a gadget like that, can we use that to speed up our algorithm? So that's how you are resolving a curse, and you can't break the curse. It's just getting out of it, or getting like avoiding it, maybe not looking at it. A related bit is that if you're just throwing more data at your problem, maybe it's like the meta learning way, that like you're making up different tasks which are, like maybe or may not be related to the problem that you're trying to solve. You augment the data, you collect more data, and then you reduce the amount of bias by taking a more vanilla approach to learning. Then this wins. And Rich Sutton wrote up this very nicely in a blog post. He calls this the bitter lesson in AI. And he notes that historical evidence shows that this is what's happening. So people tried in AI, like all kind of structured approaches, and then only now that we have a lot of compute and we have a lot of data and we put in less structure, that we see that we are getting the results that our ancestors were longing for a long time before us. But I say that this is, I think, maybe jumping to a conclusion a little bit too fast. The actual bitter lesson to me is that, well, we have a relatively short history in AI, and we have a really hard time predicting what works, what doesn't work. And I would also say that still we are not running exhaustive search today, right? So if less structure would win, then maybe you should just enumerate all the programs in an arbitrary way and then search through all programs, and then that would be the best way of solving your AI or reinforcement learning or whatever problems you have. So we don't do that. So some middle ground is necessary. So the resolution to this is that you should diversify your research. So scaling up, trying more data, less structure, yes, you should try that. You should also maybe try to look into how to make your algorithms more clever. Both are absolutely important, I think. The other thing that I would note here is that structure is always present, no matter what you do. So no matter how hard you try, some structure is always going to be there, right? So your search algorithm enumerates the programs in an arbitrary order, but that's an order, and that creates a bias. So all the algorithms that we know of, gradient descent, whatnot, you might think that, oh, it's totally unstructured, this neural network, but it does have a structure. It may look innocent, but it may not be that innocent. Actually, studying the structure, I think that that's the big deal. That's like understanding more about these algorithms. That's a really important task. Next fallacy is that we need to find and identify the best of the best algorithms. And like you see this a lot in papers, but a new algorithm is compared to all the previous ones, and it has to be the best possible on all possible tasks. This seems like a natural requirement and tendency. But of course, this may not work at all, because the best of the best often doesn't exist. So here I'm showing the graph of x times y. X is maybe the problems, and y is the algorithms. And, like for every problem, there is an algorithm which works the best for that problem, and the best of the best might not exist. So there is no guarantee that the best of the best is going to exist. Actually, for most of the interesting problem settings, I would say that no such thing is going to exist. So what are we going to do then? Well, don't stop looking for it. So all the methods have their own niche. We should aim for understanding these methods, their niches. We should aim for understanding the structure for problems and then match the structure of the problems with the niche of the algorithms. And also, if you're into this leaderboards and benchmarking, then you also have to remember to be able to do a good job at this, Goddard's law, which says that when a measure becomes a target, it ceases to be a good measure, right? So it's really hard to play this game in such a way that your benchmarks are not expiring. It's not necessarily impossible. A lot of communities are trying to do this outside of reinforcement learning, the planning community, optimization community, and so on and so forth. But I think that there is no silver bullet, and that two other thoughts are more valid than ever, that you should understand the pros and cons of each and every algorithm that seems reasonable to you. All right, so with this, we arrive at our conclusions. What's the main conclusion? Well, maybe the main conclusion is that these are all the myths about reinforcement learning. Well, what's the origin of this? Well, this talk. Maybe this is not true, because all sweeping statements tend to be untrue. So this was a sweeping statement, so this may not be true. So the other conclusion I would like you to draw from this talk is that reinforcement learning can be tremendously fun because it's challenging. And if you're interested in learning about the foundations of reinforcement learning, then there is an upcoming boot camp at the Simons Institute at Berkeley, the first week of September, basically, and you are welcome to join. It's going to be all online. And there are, of course, a lot of other good resources on the internet as well, bookshops and whatnot. And finally, the biggest conclusion should be that please stay to be critical with your own work, with other works, because a foolish faith in authority is the worst enemy of truth. So don't believe any word I say. All right. So here are some credits to some of the graphics that I took, and here are some references. And if you want to get in touch with me, then I'm available on email, and I'm going to upload my slides to my website.